In this section, we will introduce the concept of correlation. Now, we spent several lectures in the first course becoming familiar with the behavior of random variables. In particular, we looked at how we can analyze normally distributed random variables, and we demonstrated the power of the central limit theorem, which comes into effect when we perform sampling. We use process specification limits to calculate process capability, the CP and CPK indices, and we use these then to establish the baseline performance of our process in the step measure. Now, in the analyze phase, we want to understand the cause and effect relationships among the parameters, and for this, we use regression and correlation methods. And later in the course, we'll then look at how we can use these relationships to perform process improvements. In this session, we want to explain what is correlation and how correlation is used to investigate the linear relationship between inputs to a process and its outputs. We want to understand the meaning of positive, negative, and no correlation between two variables, and to explain the Pearson product moment coefficient of correlation, or RXY, and what information it conveys about a linear relationship. And just to relieve everybody a little bit, we say there's no calculation here. Not in this section. So, you want to buy a car. Well, you want to buy a used car. What are things you're interested in? Well, a lot of people are interested in the mileage on the car. So, we've got a lot of data. Maybe we'd like to have a look at how the age of the car correlates with the mileage. So here we have the age of the automobile in years and the total kilometers driven. Apologies for those who are still using miles, but I live in Germany now, so I'm going to use kilometers for this example. And here we have data. So we have XY pairs. So X is our age of our automobile. Y is the kilometers driven. And how can we look at this data? It's maybe a little bit difficult to look at just the table. Well, we could plot a scatter plot. A scatter plot means you're graphing each value of y against the corresponding value of x. And we're showing the relationship between the two variables then in a meaningful way. And if you plot our data, this is what you see. So, I think everybody understands this. Everyone can do this. You can already interpret this data. Age goes up, total kilometers goes up, pretty much. That's correlation. So, correlation analysis is a method to study the linear relationship between two random variables. And we use this in analyze. If there's a correlation between the variables, then we know how the dependent variable changes when the independent variable changes. And we all know good examples of this, like when the temperature goes up, ice cream sales go up. But we have to be careful, and I did include a picture from a nice website if you have time to look at some of these spurious correlations. Here we have U.S. spending on science and space technology, very well correlated to suicides by hanging, strangulation, suffocation. So we have to be careful. There are many examples of variables that appear to correlate. And here we don't have the XY relationship. Just to clarify, this is the suicides, this is the U.S. spending, and they both seem to have the same kind of dips. What we're seeing here is that there's something else going on. We have maybe a third variable. For example, if you can see that the number of libraries in a city increases, the number of murders increases. Now, murders and libraries don't correlate to each other, but there's a third variable. Can you guess what it is? Libraries and murders in a city? Both of them correlate to the population of a city. So when you have what's called a spurious correlation or spurious relationship, and what that means is when you have two or more variables that are not actually causally rated, there's not a cause-effect relationship, but it could be wrongly inferred that they are correlated due to either coincidence or this third lurking variable, or that's linking them. And this was a cartoon that applied then to my statistics classes. So this person says, I used to think that correlation implied causation, but I took a statistics class and now I don't think that. And the person says, well, sounds like the class helped. And he says, well, maybe. He's not sure he will now admit that there's a causal relationship. So here we have 3 examples of linear correlation. In A, what we see is that X and Y are negatively correlated. What this means is as the value of one variable increases, the other variable decreases, and you see this downward slope. In B, you see no correlation. There's no linear relationship. Now we have to be careful here. There's no linear correlation. You could have a nonlinear relationship. You could have a relationship, but you're saying that it's not a linear relationship. Here we see in C a positive correlation. When X goes up, Y goes up. So you see this positive slope in a linear fashion. So what do we have here? Well, clearly we have this sort of, as the number of years increases, the total kilometers driven, the mileage increases, so you have a positive correlation. Now, this here we're seeing the use of the scatter plots. They're very easy to see. But of course, with big data and data analytics, you can't necessarily spend your time looking at graphs. So we need to have the correlation coefficient. So the correlation coefficient gives us a quantitative measure of our correlation. And we call it rho xy. It is the standard, the covariance, this parameter is called the covariance of 2 variables, x and y, 2 paired variables, divided by the standard deviation of x and the standard deviation of y, which we've seen, of course, in the first course. Now, we haven't talked about the covariance. We're not going to calculate that in our course. But overall, basically, you're ending up with a similar calculation for the covariance, except that instead of taking, so for the standard deviations, you're taking always the average value, the difference of the average value from each value squared, and the y, the difference of the average value from each value squared, and summing them together. Here, for the covariance, you're taking the difference of the average value of the x's from each value of the x, and the difference of the average value of the y from each value of the y, and you're multiplying these two together. So it's sort of an intermediate step. The Pearson product moment of correlation, or RXY, is it's an empirical quantity. It is calculating then from each of our data points this rather long formula, and it's going to give us then a number. Now, as I said, we are not calculating this in our course. So that's why I don't want you to worry about this. This causes lots of errors. We will be calculating the coefficients for regression. It is important in part of this course that we do some of the math. I know a lot of you would say, well, the computer will do that for me. But I think also any of you have worked with data, you know that sometimes the computer can make mistakes, not because it's made a mistake, but because you've got some data that doesn't fit in there. So it is important for us to do some of these calculations, to work on our math a little bit. But of course, yes, in most of the projects, you'll be using some kind of computer program like Minitab, which would do these calculations for you. And frankly, I think RXY, we need to understand what it is. So let's move on to that. So it can be shown then that the correlation coefficient, both the rho xy and the empirical rxy, lie in the interval -1 to 1. So what this means is if it's negatively correlated, rxy will be less than 0. So rxy lies between -1 and 0. For no linear correlation, rxy would be very close to 0, and positively correlated rxy would be greater than 0. So rxy lies between 0 and 1. Now let's look again at our used car. So we've already seen we've got a positive correlation. We know how to calculate the Pearson correlation coefficient, and we've got our data. And so in a exam or something, you'd be given your data. Here we can see the sum, so 40.4 divided by, there's 12 data points here, gives us then a mean of 3.4. Here we have all the y's summed together. This is x bar. Y bar is going to be equal then to 1044 divided by 12 equals 87.0. If you want to look at this more carefully, if you use the simple expressions, then you can use these other sum data. But in the end, rxy in this case is equal to 0.80. Yippee! What does this mean? Okay, first of all, even if you don't see this data, if you don't see that at all, you can calculate this value. And so we know this lies between 0 and 1. So it's a positive correlation without ever looking at the scattered plot, without ever looking at the data. And we'll see in a minute also, 0.80 is quite close to 1. So it's actually a pretty good relationship, pretty strong relationship. But before we do that, let's look at the example from the book. Here we have the drying oven, humidity versus drying capability. And again, this reflects back to our the study of this bonding that they were performing for the cable harnesses. So here we have X, and here this is abbreviated as X sub 1, so one of the possible X's, humidity and dryability. So you've got then the sum of all the different, there's N equals 20 different values here that were measured. So they were studying this. They wanted to see how the humidity affect the drying capability of this oven. They had this dryability index that they were using. So you look at this, the data. You have to now evaluate this data. So again, you can look at all the values. You've got your equation that you can use. And in this case, rxy is equal to negative 0.58. So what do we see from that? First of all, you see that there is a negative correlation. You can sort of see this from the data. If you were sort of modeling it, you would say that looks as though when the humidity goes up, the dryability goes down. But what about this minus 0.58? How does that compare to the 0.8 we had before? So this is the next thing that we'd like you to understand. If rxy approaches 1, this means, okay, first of all, it's a positive 1 between 0 and 1. So you have a positive relationship, positive linear relationship. And as it gets close to 1, you can say it's a strong relationship. Again, as we said, as it's near 0, there's no linear relationship. And as it approaches -1, you get a strong negative linear relationship. So let's look at some examples. Here we have, for example, here we have R is 0.07, positive relationship, and 0.7 is, for example, greater than 0.3. So here, they're both positive relationships in the data, but here you can see the data is clustered around the line much more closely than here. And for R equals 0, well, the line is kind of in the middle. There's no real linear relationship there. And likewise, you can have negative values. Here, again, there's a negative relationship where the data is fairly well clustered around the line. and here it's not so well clustered around the line. So as R, in these cases, gets closer to plus or minus 1, that means the data is a better linear relationship. It's a stronger linear relationship than if you have a lower R. So if you went back to the drawing example here, this negative 0.58 is not very strong. The data not very well clustered around the line. So the last point I want to make there is, what does the correlation not tell us? So first of all, correlation tells us if it's a positive or negative relationship, right? And you've got this -1 less than or equal to 0, less than or equal to +1. You've got this idea that this is a strong negative linear relationship. Linear in here again. And here you have a strong positive linear relationship. But look at this. That's funny, right? R is 1 for both of those. Why is that? Did I make a mistake? X, Y? I mean, they're clearly not the same, right? This one looks like this. This one looks like this. But both the points lie exactly on the line. They're both positive. So R is 1 for both of these. But what you see here, it doesn't tell you anything about the slope of the line or the intercept on the y-axis. And so this is why correlation is definitely, it depends what you're doing. I mean, you may just want to know if something's correlated. But if you're looking for then how they're how they're related more exactly, you don't have enough information. This is then again where it leads us into regression. So again, correlation is telling you if it's a positive or negative linear relationship. It's also giving this idea of how strong the relationship is. So I should put 1 there, 2 there is the strength of the relationship. But it's not telling you the shape of it. It's not telling you how fast y is changing with x. It's not telling you where this relationship is located with respect to y. And that we do next in regression. And finally, this is one of the classic examples from the statistics books. Say I have something that looks like this. Y equals x squared. Now this should go through 0, sorry, this should go through 0. So 1, 2, 4, 4, 16. Y is x squared is a perfect relationship, right? I should maybe put these as data points, not as a curve. But this is y. Excuse me. Y is a function of x. Y equals x squared. There's a perfect relationship. But our xy is going to be 0. Why? Why? Did I make a mistake? No, this is not a linear relationship. And so that was the last thing you just need to remember. If there's no linear relationship, then your Pearson correlation coefficient will also end up being 0. So again, look over what correlation tells us, understand why we're using it. Could be useful in certain situations, but you don't have to calculate anything for this.